All right, so today we're going to do something a little different. We're going to open up the Language Engineer's Toolkit. Now look, we're not just talking about using languages like Java or Python. We're going to see how they're actually designed, what makes them tick, and why they're built the way they are. So yeah, let's pop the hood and see what's really going on inside.
So you're probably spending your days, your nights, writing code, right? Solving problems, building some awesome applications. But have you ever just stopped and thought about the tools you're using? I mean, really thought about it. Why does Java feel so different from Python? What are the actual rules, the principles that are running the show behind the scenes? Well, that's exactly what we're going to get into.
Okay, first things first. Why should you even bother with all this? I mean, isn't it enough to just know how to code? Well, here's the thing. Think about any skilled professional, right? A good mechanic doesn't just know how to use a wrench, they understand how the engine works. It's the same for us. Understanding how our tools are built is what separates a good programmer from a great one.
And trust me, this isn't just some boring theory. The benefits are super practical. Knowing this stuff, it helps you write way better, more efficient algorithms. It gives you more tools in your mental toolbox for solving tricky problems. You'll be able to choose the perfect language for a new project instead of just using what you know. And this is the real game changer. It makes picking up new languages so much easier.
And that leads us to a really key idea. See, programming languages don't just appear out of nowhere. They're built for a purpose. They are specialized tools designed to solve a specific kind of problem. I mean, you wouldn't use a hammer to saw a board in half, would you? Of course not. It's the exact same idea here.
And you can really see this in action when you look back. So, for example, way back when you had Fortran. It was an absolute monster for heavy-duty scientific math. Then, for the business world, you had COBOL, which was all about making reports and handling decimal numbers perfectly. For early AI, Lisp was the king of symbol manipulation. And for systems programming, the code that runs your operating system and needs to be crazy efficient, you had C. Each one was the right tool for that specific job.
All right, so we've got all these different languages, all these different tools. But how do we decide if a language is actually good? What's the checklist? What are the things we should look for when we're evaluating a programming language? Let's break it down.
First on the list, and this one is absolutely massive, is readability. Here's a little secret about programming that they don't always tell you. Code is read way more often than it's written. If you come back to your own code 6 months from now and can't figure out what it does, you've got a big problem. And if your teammates can't read it, forget about it. Simplicity, clear syntax, that's what it's all about.
Okay, next up is writability. This is kind of the other side of the same coin. How easy is it to get an idea out of your head and into the computer? A language with good writability just flows. It doesn't fight you. It lets you build things and hide away the complex bits. That's what abstraction is all about, so you can focus on the big picture.
And last but not least, reliability. This is the big one. Does the program actually do what you told it to do? Does it crash? Does it give you weird, unexpected results? You know what I'm talking about. This is where things like type checking come in. Stopping you from accidentally trying to add a number to a word, or having solid ways to handle errors when things go wrong. That's what makes a language reliable.
So now we have a checklist for what makes a language good. But let's take a step back. What actually influences how a language gets designed in the first place? What are the blueprints they're built on? And maybe more importantly, what are the tough compromises language designers are forced to make? Well, believe it or not, the single biggest influence on pretty much every programming language you've ever touched is the hardware, the computer architecture itself. Specifically, something called the von Neumann architecture. This has been the fundamental blueprint for almost every computer since the 1940s. And languages like C, Java, Python, they are all built around the way this architecture works. And at the core of this whole design is a really simple rhythm, almost like a heartbeat. It's called the fetch-execute cycle. The processor grabs an instruction from memory. Then it figures out what that instruction means. Then it does it, and then it just repeats over and over. Fetch, decode, execute. That's it. And our programming languages, they're basically just sophisticated ways for us to control that cycle. A variable is just a nickname for a memory location, and an assignment statement is how we tell the computer to stick some data in there.
Now this design is brilliant, but it has one major weakness. It's called the von Neumann bottleneck. The best way to think about it is like a massive traffic jam on a highway. You've got the super fast processor on one side and the slower memory on the other. The processor's just sitting there ready to go, but it's stuck waiting for data to get shuttled back and forth. This bottleneck puts a ton of pressure on language designers to be as efficient as possible.
And all that pressure leads to one of the most important truths in all of software engineering. Every design is a trade-off. You just can't have everything. It's a constant balancing act. If you make a language super safe and reliable, you might have to give up some raw speed. If you make it incredibly fast, you might sacrifice some readability. It's all about making choices.
Let me give you a classic example of this. Readability versus writability. There was this language called APL, and it had these unbelievably powerful operators that let you do crazy complex stuff with just a handful of symbols. I mean, from a writability standpoint, it was amazing. The problem? The code looked like complete gibberish to anyone else. It was basically a write-only language. They cranked writability up to 11, and readability went right out the window.
Or how about this one? Reliability versus cost of execution. Think about Java. Every time you access an element in an array, Java does a little check behind the scenes to make sure you're not going out of bounds. This makes the language super reliable. It saves you from a whole class of nasty bugs. But that check isn't free. It takes a tiny bit of time. And when you're doing that millions of times in a loop, those tiny bits add up. That's the trade-off right there. A little bit of speed for a lot more safety.
Okay, so for our last section, let's talk about the final piece of this whole puzzle. How does the code that we write, the text in our editor, actually become something the computer can understand and execute?
Well, there are basically two main ways this happens: compilation and interpretation. With compilation, you take your entire program and run it through a special translator, a compiler. It chews on it for a while and spits out a new file of pure machine code. That translation step can be slow, but once it's done, the program runs incredibly fast. On the other hand, with pure interpretation, there's no big translation step. An interpreter just reads your code one line at a time and executes it right then and there. It's faster to get started, but the overall execution speed is way, way slower. We're talking 10 to 100 times slower.
So, to try and get the best of both worlds, a lot of modern languages like Java and Python use a hybrid system. What happens here is your code is first compiled, but not into machine code. It's compiled into an intermediate language, something like Java's bytecode. Then, a special program called a virtual machine interprets that bytecode. This gives you that amazing portability, the whole write once, run anywhere idea, while still being much, much faster than just interpreting the original code from scratch.
And that kind of brings us to a final, really cool thought to leave you with. Everything we've talked about today, pretty much all of it, is based on languages built for that von Neumann architecture. But what happens when that's not the only computer we have? We're on the verge of building totally new kinds of machines. Quantum computers, computers based on neural networks. So the big question is, what will the programming languages for those computers look like? I have no idea, but that is the next great challenge for language engineers.